Okay, so now if we then bring that value of T1 from 59 to 59.5, we'll bring it a little bit closer to 60, thus making that interval shorter. The time interval is now 0.5 seconds. And V of 60 again is still 400. And V of 59.5 is 406.69 and 4 fours. Can't squeeze it really in there very well. Which gives us negative 6.694444. So when we divide negative 6.69444 by 0.5, we end up getting negative 13.388. Okay, so please continue working on this. We're now bringing T1 closer to T2. So now instead of 59.5 seconds, we're going to change it to 59.9 seconds, which is even closer, making that time interval even smaller. So that time interval, when we subtract them, is 0.1 of a second, or a tenth of a second, and we're going to have 400 minus 401.334444, and that equals negative 1.33. Okay, I know there's lots of decimal places, but it's going to be important to see this progression here. And when we divide, we get negative 13.344. So as you can see, things are starting to develop here. So what I'd like you to do now for the next T1, we're going to change this now to 59.99 and leave T2 as 60, and then the last T1 is going to be 59.999. Okay, so we're going to bring it up to 1/1000th of a second difference between the two to make that time interval very, very close. Okay, so I'd like you to continue calculating. Well, V of 60 is already done, and then just calculate V of 59.99 for this next row, subtract, get the delta T, and then divide them, and then do 59.9999, sorry, 999, just 3 nines is fine, and get that change of volume divided by the change of time here, and then get your delta V over delta T. Okay, so after you would have paused the video, you would have got this mess of numbers here, and so we end up seeing that the delta V over delta T is sort of zeroing in on negative 13.333. Okay, so now what we're going to do is, so that was the preceding interval where the time T1 was 1 minute before, in that minute before 60 minutes. Now we're going to use a following interval. So this technique is the preceding and following intervals. And this is technique 1, part B, where T1 is going to stay at 60 and T2 is going to continually change, starting at 61 and slowly decreasing, getting smaller and smaller towards 60. And so the same kind of idea as before. T1 staying constant at 60, T2 is going to be changing, 61, then 60.5. We're going to change this to 60.1, and then we're going to change that to 60.01, and then finally to 60.001 to keep the same level of accuracy as the preceding interval. And we'll calculate V of 60.1, subtract V of 60, and actually this should be 60 also right here. I made a slight error there. And then make that calculation, please, and then we'll do V of 60.01 minus V of 60, continue with that, please. So please continue working on that table and fill out all those values. So please pause the video now to work on that. And now that you're back, please take a look at this table, the completed table, and again take a look here, now that you've finished that, where the values of delta V over delta T are, they're decreasing further from negative 13.222 all the way down to negative 13.333, whereas the values in the preceding interval were increasing from negative 13.444 up to negative 13.333. Okay, so notice that in both sides, preceding and following, the two rates of change are zeroing in on the same value. Okay? So by observation, the general trend of the average rates of change of volume, the final column of the table there, of the hot tub approaches, as you can see, negative 13.333 liters per minute, which is verified by taking the average of the last entries in the final column. So what we're going to be doing is, if we take the average of the final two rates of change for the preceding and the following interval, take the average of those two values, that will give us a very good estimate, catch that? A very good estimate for the instantaneous rate of change. It's important to note the trend of the rates of change in both the preceding and following interval, as the time interval preceding and following 60 minutes gets smaller and smaller, approaches zero. By using this technique, we can't calculate the instantaneous rate of change itself, but we can calculate an estimate of the instantaneous rate of change. So this example demonstrates estimating the instantaneous rate of change by keeping one point fixed and continually moving the other point closer to the fixed point.